and I'm going to tell you a little bit about some work we did as a part of a bigger project funded by DARPA called SafeDocs, which aims to try and improve the situation of parsing. So why are we talking about parsing in 2024? And well, the problem is that parsers are kind of everywhere. There's pretty much no application that doesn't do some kind of parsing. And they are usually at the very kind of boundary of an application. If you're going to start attacking an application, you're going to be interacting with a parser of some sort. And furthermore, if the parser is incorrect, many exploits are based on like the parser doing something wrong. And they're not easy to get right, even though we have a whole bunch of tooling and a whole bunch of work has been done. Mistakes happen all the time. I mean, if you kind of follow security things, parsing vulnerability, if you're going to exploit a system, I was going to look at the parser first. And so as we looked at various kind of parsers, we identified roughly 3 different kind of classes of bugs in parsing code. And so the first one is just an actual implementation bug in the parser, right? That typical, there's a buffer overflow, whoever wrote the parser didn't consider some sort of input, and then a malicious attacker gives it bad input that you're not supposed to give, and the parser, crashes or gives you access to some kind of internal data. The second very common thing is that, well, how do you know if your parser is correct? So usually there is some kind of specification, but oftentimes these things are big and are written in English, right? So there is some kind of big document that describes what the format you're parsing should do. But for this project, like for example, we were kind of interested in parsing PDF documents, and the spec for that is over 200 pages long. It's really big. And oftentimes, even though the PDF spec has been designed over years, so it is very precise, still we found things that are missing or unclear or ambiguous. So many parsing mistakes are simply because somebody misunderstood how things are supposed to work. And then what that leads to is like a mismatch, because parsers are not a standalone application. They're usually part of a bigger system. This kind of misunderstanding of the specification often leads to kind of different assumptions that the application code has and what the parser actually checked, and that's how you get exploits. Okay, and so currently there are kind of, as I said, there's been a lot of work, and in general, if you look at like regular expressions and context-free grammars, these are the things that have been studied, and the theory is very, very well understood. Most programming languages usually have some kind of tools to support those. So there is typically some kind of library to do regular expressions, or some kind of a tool like Bison or Yak, or in Haskell Happy, in Antler, and tools like that that would kind of take a context-free grammar and compile it for you. So oftentimes this kind of gets rid of at least the kind of bugs in the generated code, well, at least in the kind of structure of the parsing code, not in the kind of application-specific code. Typically, they all use different notations, but for these things, they're more or less the same. Usually, if you know one of them, you can kind of pick up what it means in another language. Interestingly enough, many compilers still don't seem to use those tools, and I kind of looked around, but like GCC, Clang, Rust compiler, they all come with handwritten parsers. And you kind of look around about why that is, and it's not very clear, but some seems to be concerned about efficiency, because these compilers have been developed for a long time, and even though machines are fast now, before they weren't. Good error reporting is oftentimes difficult with those tools. So yeah, I don't know if anybody has more insights. I was quite surprised to find out that they don't have grammars. But however, on our project, we were more interested in processing the so-called binary formats. So these are more formats not where white space doesn't matter so much. They're more structured, more like PDF documents, Word documents, things like that. And there is a whole lot of tooling to support these tools, but there is no standard notation as far as we can tell whatsoever. The tools oftentimes when you process binary data are very performance oriented. So speed is what matters, and validation usually is kind of left to the application. So the job of the parser is more or less to figure out where the data is in a document, and then the application is supposed to parse it. And a lot of the tools we found kind of don't aim at parsing whole documents, but they're much more at processing like little packets, so simple struct-like structures. And when you get into more complicated whole documents, really the job is kind of split between the application and the parser, and they have some kind of a complicated sort of interaction. And so specifically these binary formats, the kind of things that make them particularly difficult for traditional parsing technologies is that they usually have a lot of data-dependent parsing. That means that you parse something from the input, and what you do next depends on what you parse. So it's not like a static structure. It is the traditional encoding of sequences is, you know, you parse a number, and then you parse that many things. Then quite a lot of formats appear to have this non-sequential parsing. So you don't just start at the beginning of the document and go left to right the way you would parse perhaps a programming language. Instead, very often you have these kind of tricks where the objects are spread around the file or something. Sometimes they're even in a different file. And you have a table of contents kind of at the beginning that tells you where things are. So to parse things, sometimes you have to parse a little bit here, a little bit there. And obviously, that's quite different than what tools like YAC support. And finally, especially in PDF, but other tools do that, oftentimes you don't even parse the bytes in the file directly. Instead, you parse, that's kind of a form of dependent parsing, but very complicated one is like you parse the data, and maybe the data is compressed or encrypted, and then you decrypt it, and then you parse that. So you're kind of parsing input that doesn't exist, you know, directly. Okay, so these things make it tricky, but you know, people have written parsers like that, and I think a particularly good way to do that in languages like Haskell and in many other languages, people have written parsing combinator libraries. So these are libraries that help you write parsers by hand, but they provide a lot of common patterns, right? So you don't have to invent everything from scratch. And I kind of looked at some of the source code for big compilers, and they don't use parsing combinators. But I think that if you're going to write a parsing by hand, using something like a parsing combinator library is a very good idea because you at least provide some structure there. Usually they're very expressive because usually parsing combinator libraries are just embedded in a host language, and you have the full expressivity of the host language to do whatever you want. Some challenges, though, they're non-portable. So every language has its own. Like in Haskell, we have 3 or 4. In Rust, there's GNOME or something. For C, there's Hammer. But yeah, they look nothing alike. I mean, you recognize some kind of functions. And also, they're pretty difficult to analyze because analyzing the parser amounts to kind of analyzing basically an arbitrary program embedded in a general purpose language. And reasoning about those is hard because they are supposed to do very many things. And finally, depending on the parsing library, oftentimes you see this kind of mixing of what's parsing and what's application logic because you're just writing a program. I find that in Haskell that is generally a little bit better because we have monads and whatnot, so you can see at least what's parsing code and what's not parsing code. But when you go to languages like Rust or C, it really kind of gets pretty mixed up usually. And so this kind of leads to our idea, the way we kind of thought to approach this problem of parsing document formats is we decided to kind of abstract this idea of parsing combinator into a standalone parsing DSL that we call Daedalus. Okay, and the focus of Daedalus, the idea was that we can use it as a specification language for specifying binary formats. So the hope, if Daedalus gets picked up, is that, you know, when you kind of define a new binary format, you can provide a Daedalus specification that should be a lot more formal than just writing it by hand. So Daedalus should be readable, importantly. The design, it is very much inspired by parsing combinators in Haskell. So if you've seen those, the things here should be pretty familiar. But because, you know, it's a domain-specific language, we've added a whole lot of patterns that are just convenient, some nice notation. It is not as general as Haskell. It's a much simpler language, but it is based on a purely functional programming language. And the idea is that also we provide backends that compile Daedalus specifications to efficient code. So I'll tell you a little bit more about that, but at the moment we have 2 backends, one to C++, one to Haskell, and we hope to add more, specifically Rust next. So let me give you a flavor of what Daedalus is. So Daedalus, as I said, it's inspired by Haskell, so it basically contains 2 sub-languages, you can think of it, that share a common syntax. The one is an effectful language of parsing. That's kind of when you specify a grammar and you say parse this thing, then parse this thing, then parse this thing. And then it has a purely functional computation language for constructing semantic values. So what a semantic value is the result of a parser, basically. You can think of it as the parse tree or the representation of your packet, something like that. And so with data-dependent languages, you need to, like with tools like Antler or Bison, they don't support data-dependent language, and because of that, the semantic values are built in the host language, right? You write your grammar, and then you say, when you match this through, this is what you do. Here we have to do this part in the language because you can depend on it. So the grammar needs to be able to understand the values you parse so that you can make dependent decisions. The language itself is pretty standard. We try to not innovate there at all. So it has a Hindley-Milner-based type system with qualified types, much like Haskell, a lot simpler than Haskell because there's no general type classes. We just have built-in classes. Supports polymorphism and type inference. It's all statically typed. And the type system explicitly keeps track of this kind of, this is a parser, this is not a parser, and you can't mix them. Also, it's extensible in the sense that we have a foreign function interface. We found that in practice this is really important to have because, as I said, these formats oftentimes, for example, require you to do decryption. And we didn't want to implement the decryption algorithm in the parser. There's already standard libraries to do that. But while you're parsing, you need to call into this library. And so yeah, we have a foreign function interface. Okay. So this is what the Daedalus declaration looks like. It is pretty simple. The def is a keyword there that says we're defining a parser. The way you know it's a parser is we have a syntactic convention. The parsers start with the capital letters. Block means we are sequencing. It is very similar to the do notation in Haskell. Let h equals header means run the parser header and name the result h. And then, perhaps not surprising, body h means parse the body. That's another parser, but this parser now depends on the value, right? So how you parse the body would depend typically on what's in the header. So that's a very common pattern, and then you define header and body in some way. So this kind of having essentially, if you will, grammar productions parameterized by value is how we get data dependence. So if you're familiar with monads, this is your standard monadic parser. One thing that is interesting is the Daedalus is not exactly monadic. I mean, certainly it has things like bind, like this block thing is sequential, and we have parse the empty thing, which would be pure return in a monad. And parsers may be parameterized by both values and other parsers. So you can have productions that are parameterized by other productions. So you can define part a list of x, where x is another parser. What we don't support is parsers that return other parsers. So parsers can only return semantic values. So there is kind of a strict distinction between values and parsers. And if you will, the type of parsers is of kind value to parser. And that does not allow you to type things like the join operation, which is the mathematical definition of a monad has this, requires a parser that returns a parser and flattens it. You cannot express that in Daedalus. It's kind of an interesting construct that I'd like to spend more work in the future studying. It's a kind of first order monad and seems to be somewhat related to this work on call by push value. If somebody has ideas, I'd be happy to talk to you afterwards. And it is very convenient because it makes code easier to compile, but also enables us to have this kind of applicative notation where instead of having to explicitly sequence things, we allow you to write things in an expression form, and based on context, the program would automatically know, okay, body expects a value, but it's been given a parser here, so I'm going to sequence them for you implicitly. In this way, you get a lot of grammars that you avoid naming intermediate values that are kind of used one time. It's pretty natural if you're used to kind of working in an imperative language to mix this pure and effectful things. Here we allow you to do that, but we are still tracking that you don't make mistakes. As another little example of what a simple Daedalus specification looks like, we have this a lot of iteration constructs, but one of them is this many construct. And by the way, in this code, I make use of this kind of syntactic sugar for mixing parsers a lot. To parse a number in base 10, many is a loop, you can think of it, that is stateful. It has a piece of state called n there, and the body of a loop can mention the state n, and will compute the new value for n. And you kind of apply the body of a loop until it fails. So the body of a loop is a parser here. So to parse a digit, you first parse one digit, and that's your initial state. And then to parse the next digit, you multiply by 10, and you add one more digit. And this is how you parse base 10 numbers. And you can easily see how to generalize that to other bases. To parse a digit, we have some special notation. So we support character classes and things like that. We support casting. So when you match bytes, you by default get a byte. We have a notion of a byte, but Daedalus knows that it's safe to turn a byte to an int. It would complain if you try to turn an int to a byte, but we also support dynamic checks to do that. So this is not, like if you're interested in Daedalus, there's more details in the paper, and we have a user manual and a tutorial and whatnot. So this is supposed to give you a flavor of the language. How am I doing on type? OK, we also support, we have a bunch of primitives for stream manipulation. So as I said, oftentimes you need to parse code that is non-sequential or even code that is produced as a computation. So we expose basically the input stream directly to the user. Basically, stream inputs are a first-class value. They're a normal value just like integers or booleans and whatnot. And you can store them in your parsing input if you want to have some stuff that's unparsed and you want to parse it later. Or if you want to code to the application to decrypt something and then change the input to the result. So by default, this is pretty low level, and if you use this a lot, leads to parsers that are very confusing to analyze. So we try to use it very sparingly, excuse me. And we opt instead for, in our standard library, we kind of have a bunch of patterns that we have identified. For example, chunk NP is a common pattern that it's a little bit like I want to parse a token that is the next 10 bytes processed with P. And it will kind of advance the input by n bytes. And it will fail if there's not n bytes and so on. Daedalus has a lot. OK, I'll wrap up. It has a whole bunch of other features, check, cast, whatever, that these are described in the paper. We have a compiler for Daedalus, which is pretty efficient. And the compiler has, as I mentioned, 2 backends for C++ and Haskell. We have a couple of other tools that analyze the Daedalus grammars and can kind of detect cavities in documents. So the benefit of having a standalone language is that you can analyze it a lot easier. We did some evaluation, and our parsers, our compiler is pretty fast. It seems to be a bit faster than a bunch of, on these simple examples anyway, other tools. I wouldn't take that as being great, but the point is here that the generated code, so the thing in brackets there is the parsing in megabytes per second. So we are faster than all of those things, but you know, on these little examples, in general, we are, I expect, in the same kind of ballpark as other tools. Yeah, so the performance is good for both the C++ and the Haskell backend. And I think that's pretty much it. In summary, I wanted to say that processing binary files is difficult, and parsing combinators, I think, are a good way to deal with these very kind of exotic formats. But it is good to have a language that is not language independent, like a language that is specific to the parsing. And purely functional languages are good for that. And hopefully, Daedalus can serve this person. We have an efficient compiler for it. And yes, as I said, we're still working on it. We are hoping to add a new backend for Rust soon. If you're interested to learn more about it, the repository is it's all open source. It's on our GitHub, and the documentation is all at this URL as well. There is a user manual for the language and tutorial. and I'd be happy to take any questions.
Great, thank you very much. Let's thank Iavor for the talk. While our next speaker sets up, we have time for maybe one quick question if someone wants to run to the mic. Anyone can see some movement. No one is running to the mic. I have a quick question, Iavor. Okay. So is there any way for people to adopt this gradually? Like say they've got a big program that's using an existing parser that they wrote. Is there a story for somehow how to migrate to using Daedalus?
Yeah, you can. Daedalus just generate, for example, the C++ backend. You can write a bit of parser and to generate some C++ classes for you. So if you want part of the parser to be written in Daedalus and the rest to be written manually, you can totally do that. Yeah, how you structure it, it's yourself. It's up to you, yeah.
Okay, great. Thank you very much. Let's thank the speaker again.
Yeah.